Hi guys, it's your guy Olumide, and today we'll be solving another one of the most commonly asked tech interview question, the lowest common ancestor. It is a DSA problem that's most commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, and Microsoft. The problem statement states that return the lowest common ancestor of two nodes, P and Q, in a binary tree. The lowest common ancestor is defined as the lowest node that has both P and Q as descendants, and a node can be considered as an ancestor of itself. So, what this problem statement is just trying to tell us is that we are trying to find a node that is actually common to two nodes, or let me say that is a common ancestor to two nodes. So now we can see that in this given example tree, binary tree that was given to us, we see that P is actually at node 8, so meaning that P represent our node 8 and Q represent our node node 8 represents P and node 7 represents Q, right? So now we see that considering these two, the lowest common node that is actually an ancestor of both P and Q is this node 3. So this is simply what we want to find, the lowest common ancestor of two nodes P and Q in a binary tree. So we are given some constraints now that will actually enable us to solve this problem, and is that the tree contains at least two nodes. So meaning that we can at least get the lowest common ancestor at any point. You understand? However the tree is going to be given to us, it is going to be possible to find the lowest common ancestor because it's going to contain at least two nodes. Definitely these two nodes is going to be the P and Q that we are trying to find their ancestor. Okay, another constraint is that all node values are unique, right? All node values are unique. So, and that actually gives us an edge. It gives us an edge, but you're gonna see it in the problem as we move further into solving this problem. Well, let me just quickly paraphrase. The edge that it gives us is that if all nodes can be unique, definitely we can know that even by the node value we can easily check if imagine if the node value of P is 8 and the node value of Q is 7. So we know that there is no other 8 and 7. So whenever we come across a 8, we know that's definitely P. Whenever we come across a 7, we know that's definitely Q. So another edge is that P and Q represent different nodes in the tree. So P and Q will not be the same. So these are constraints that is given to us that will enable us to solve this problem further. Now, one strategy to solve this problem is to traverse through each node in the tree one by one and to check whether the current node at any point, meaning that any node at any node, whether that particular current node is an ancestor of both P and Q. So meaning that we come here, we try to check if it's an ancestor of both P and Q. We come here, we try to check if it's an ancestor of both P and Q. We come here to this node also, we try to check if it's an ancestor of both P and Q. To make this check, this evaluation, then it is crucial that we know the condition that a particular node needs to meet for it to be an ancestor of both P and Q. That is, for it to be the lowest common ancestor of the node P and Q. So let's start by discussing where P and Q will need to be for the current node to be an ancestor or to be a lowest common ancestor of those P and Q. Consider the binary tree below. This binary tree now. So let's find out where P and Q need to be for this node 3 to be an ancestor of P and Q. Node 3 is going to be an ancestor or lowest common ancestor of P and Q if P and Q are actually present in node 3 subtree, right? So if they are present in node 3 subtree, and what I mean by node 3 subtree is that if they are actually in the left subtree or right subtree of node 3, then definitely node 3 is actually an ancestor of both P and Q. Now let's identify where in the subtree that P and Q, fine, we already talked about the fact that for node 3 to be an ancestor, then P and Q have to be in the subtrees of the node 3. Now let's identify where in the subtree that P and Q needs to be for it to be for node 3 to be the ancestor. Now in this visual, we see that it's either one of P and Q is in the left subtree of node 3 and the other is in the right subtree of node 3, or one is at node 3 itself, meaning that node 3 is actually a subtree itself. And what I mean by that is that, don't forget, in the problem statement it is given to us that a node can be an ancestor of itself, right? So, and therefore if we are looking for, imagine if P is here now, you understand, and Q is here, we can still say that node 3 is the lowest common ancestor. Why? Because it actually contains P and Q, right, in its subtree, even though it is its left subtree. What I'm trying to say in essence is that the node that is the lowest common ancestor could be an ancestor for both P and Q, for either P and Q. Why? Because a node can be considered as an ancestor of itself, right? So and that's what brings us to the fact that either one of the P and Q is at the left while the other one is at the right, or one is at the left subtree while the other one is at node 3 itself, while one is at node 3 while the other one is at the right subtree. So these three conditions whereby they are at the left and right subtree, or at the current node and the left subtree, or at the current node and its right subtree. So now you will notice that in these cases whereby node 3 is the lowest common ancestor, this is because in each of these cases there is not a node that is lower than node 3 that contain P and Q as descendants, right? Why? Look at this situation now. You see that apart from node 3, there's no node again that is lower than node 3 that contain both P and Q. No. So that's what we mean by the lowest common ancestor. So we are not just finding the ancestor, we are actually finding the lowest common ancestor, meaning that the one that is lowest, right? So because imagine putting it at node 6 right here. Node 6, fine, is an ancestor of P, but is it a common ancestor to Q? No, it is not. So 3 is the actually an ancestor that is lowest and is common to P and Q. Now to further buttress that point, let's imagine a situation whereby P and Q are in just one subtree, maybe the left subtree. Now let's say this node 8 and node 9 are our P and Q. You will see that node 3 is no longer the lowest common ancestor. Why? Because there's now a node or an ancestor lower in the binary search tree that is lower to node 3 and as well contain is common to both node P and Q. That is, it contains both P and Q. So what I'm trying to say in essence is that in this situation like that, we see that node 6 will actually be the common lowest common ancestor. Why? Because because it is the lowest node actually in the binary tree that contain both P and Q. So it's not gonna be node 3. So for it to be node 3, it actually implies that one has to be at the left subtree, and one has to be, I mean, for this particular case, for this particular tree, one has to be at the left subtree, right, while the other has to be at the right subtree, or one has to be at node 3 itself and be at the left subtree, and one has to be at node 3 itself and the right subtree, something like that. Because according to this tree, if both of them actually falls in this left subtree, definitely, let's say it falls at 8 and 9, right, node 6 is going to be the lowest common subtree in that case. So we are actually not just taking ancestors, we are interested in the lowest common ancestor. Now an observation we can draw from what we have considered so far is that if the current node, say node 3, so if the current node is going to be the lowest common ancestor, then P and Q, or if it's gonna be the lowest common ancestor of P and Q, then P and Q will be found in exactly 2 of the following 3 locations. So it's gonna be found at the current node itself, I mean either P or Q. It's gonna be found at the current node itself, or it's gonna be found at the current node left subtree or the current node right subtree. So what I'm trying to say is that just 2 out of these 3 conditions, any 2 is going to be satisfied for a current node to be the LCA. Is either 2 out of the following, whether the current node is whether P and Q is P or Q is actually the current node itself, while the other one is the current node left subtree, or it is one is the current node itself while the other one is in the right node subtree, or one is in the left subtree and one is in the right subtree. So 2 conditions out of these 3 is what we need to be true, right, for that current node. Don't forget, you say that current node is common to all of them, either in the current node left subtree or in the current node right subtree, or in the current node itself and current node right subtree, or in the current node left subtree and right subtree. Those any 2 conditions out of these 3 now is what we need to evaluate through for the current node to be the LCA. Now what this means is that by traversing the tree node by node and checking if P and Q are present in any 2 of this location, mean that if they evaluate true for each node, right, for each node they're gonna check if P and Q are present in any 2 of this location, we can effectively get the DSA the LCA, right? So you can effectively get the LCA. And to solve this problem, the depth first approach will be better because it enables us to navigate through the and traverse through the tree, node by node, right? So and then all we just want to do is whether the current node is P or Q, right? So meaning that don't forget that each of the nodes are unique. P is not equals to Q. Definitely if the current node can be P or can be Q, or it can't be P and Q together, so we just need it to be just a single out of the P and Q, while we go on to search for the other one in these two positions now. So so the first thing we wanna check is if it is P or Q. The second thing we wanna check is if its left subtree contain P or Q, and then if its right subtree contain P or Q. So if any 2 can evaluate true out of this expression, probably this and this, maybe the current node is P or Q and then the left node contain P or Q, it definitely means that one is P, one is Q. So, or if the left contain P or Q, the right contain P or Q, that you just need any 2 out of these 3 conditions to be true. And once it is true, we then could guarantee that particular current node whereby 2 of these conditions evaluate true is our LCA. So, and then for the return statement now, we actually return true if any of the 3 variables are true, as if any 2, right? Okay, fine. You might be wondering that, okay, what do we return? The thing is that we are going to consider it in this structure that we have here, but to returning is actually different from the LCA, right? LCA is when any 2 out of the 3 positions evaluate true, right? But for the return is actually if any of the above 3 variables are true, because this will indicate that either P or Q are in the current subtree, and it is by that we will be able to compare it with its parent left subtree. So if it's, imagine now a particular node, or let me say particular subtree evaluate true, right, meaning that P and Q is in that particular current subtree. So, and that is we can only guarantee that if any one of the above variable is true, definitely we know that either P or Q is in that one. So fine, that particular tree is not the LCA probably, but that way we can be sure that probably its other subtree, probably its other left subtree could contain the other one, right? And that way their parent now is gonna be the LCA, something like that. So the return statement is that for each of the left child and left subtree and right child and right subtree that we are going to be considering, if any of them satisfy the condition, whether it contains the node or it's contained in the left subtree or right subtree, we are just going to return true, right? So, but there are going to be 2 conditions. I don't know how to put it, but if it returns true like that and another subtree returns true, definitely probably its corresponding left or right subtree returns true, then we can say that their common parent is the common ancestor. Let's consider this example now and look at their return, right? Okay, looking at this particular node now, we are gonna use DFS to navigate to the bottom here. So let's say we are basically starting from the bottom now and at the root node. So at the root node, so which is node 4, we see that our P and Q are actually node 8 and node 7. So because they are not, node 4 is not equal to 8, we are gonna return false to we are gonna return false, meaning that for this particular node it is not the lowest common ancestor, and it is not even either P or Q, right? So similar thing here, we are gonna return false because this is 5. Now if this node 2 right here, try to check the left node and the right node and see that both of them are false, definitely there is no how the LCA want to abide there. There's no how node 2 want to be the LCA, because two out of this position must be met. Either node 2 is a P or Q, or its left node and its left node is a P or Q, or either node 2 is a P or Q and its right node is a P or Q, or either the left node and the right node are P or Q. So because none of these conditions are met, it's gonna return false again back to so the for this particular subtree, left subtree of node 1 is false, right? So and then similar things, the DSA is gonna come here to evaluate the left and right here. Now you see that this particular left node evaluate true, so true will be returned here. Why? Because it actually P is either P or Q, so true is returned here. So you see the essence of returning true. That true does not basically mean that node 8 is a lowest common ancestor, right? But it means that it is either a P or Q. So now that true is returned here, now node 9 will be tested as well, but because node 9 is not a P or Q, it's gonna return false. So fine. Node 6 is actually not a P or Q, so therefore we can't say that this one too is not returning true. But because there's a true right here, it means that this whole subtree at least have a P or Q, so we're gonna return that true again to this node 3 up here, right? So considering the node 3 right node now, it's actually a Q, and because it is a Q, it returned true. Now because the left subtree, one of the conditions have been two of the conditions have been met, which is the left subtree of node 3 is true and the right subtree of node 3 is true, definitely node 3 is the LCA. So we can just move on to return true here. Why? Because one of them evaluate true. So it's two different things, right? We are gonna return true from a particular node, be it a left node or a right node, be it a left child or right child, if we can find P or Q in that particular subtree. So that's what I mean here when I say that we return true if any of the above three conditions are true. So you see that returning true here, you understand, or returning true in any other place does not guarantee the LCA condition to be met. It just actually guarantees that one out of the left and right child or left and right subtree is true. So if it is, return true. But particularly if the left subtree and right subtree is true, or the current node and the left subtree is true, or the current node and the right subtree is true, definitely we found our LCA. So that one is we are going to be using a variable to represent that one. That one is not actually a return statement. So you are going to see it in the code implementation that we are going into now. Alright, let's move into the code implementation for the lowest common ancestor of two node P and Q. First, we'll be defining the tree node that will represent our node class. It has the attributes value and that represent the value of the node's value, and also have the left and right attribute that represent the left and right children of the node. So we say that the left and right is initialized to none at first. So now, considering what you can see on the screen, right on the screen, we have some node that is defined. We are trying to represent that structure in code format now. So we have node 1, node 2, node 3, node 4, node 5, node 6, up to node 9, and now we have this connection between them, whereby node 1 have a left child of node 2 and a right child of node 3. Node 2 have a left child of node 4 and right side of node 5, and so on, as you can see on the screen, the structure. So alright, let's move on to into the code implementation, but before then let's define our P and Q. Let's say our P is node 7 and node, let's see, our P is actually node 8 from the problem statement, node 8, while our Q is node, is that node 9? Let me check. Our Q is node 7, actually node 7, right? So now we'll be defining a function lowest common ancestor. It will take in the root node, which is node 1, right? And it's gonna take in P and Q, so it's gonna return the lowest common ancestor to P and Q. So let's quickly define the function now. Function lowest common ancestor is gonna take in the root node, so which is actually a tree node, right? It's gonna take in the P, which is also a tree node, is also a node, right? And it's gonna take in a Q, which is also a tree node. So now the return is going to be an integer, which is going to, right? Okay, it's going to be a tree node as well, which is going to be the lowest common ancestor, which is a node, the lowest common ancestor to P and Q. Okay, we are gonna be calling the function DFS, right? DFS of DFS. So this function is what we're gonna be, is like lowest common ancestor is a wrapper to this function DFS, and so it's going to be taking in the root node, and the root node is gonna take in the P and the Q. But before we do that, let's define a variable, a global variable that is going to help us to keep track of the LCA, because if you could remember, I talked about in the logic, I talked about the fact that what is being returned by the function, this recursive function DFS that we're going to be defining, what is going to be returned is just a true or false, right? So, and if any of the three conditions is met, it's going to return a true. But for a particular node to be a LCA, to be the lowest common ancestor, it requires that at least 2 is met. So you see that there's not a difference. This function DFS is going to be returning true if just a single out of the 3 conditions are met, as I explained in the logic. That is, if the P and Q, if the P and Q are actually in the left and right subtree of the current node, or probably one is at the current node itself and the other is at the left subtree, or one is at the left node itself, or one is at the right node and the other one is at the current node itself, right? That is, one is at the current node and the other one is at the right subtree. So 2 out of this condition have to be met for that particular node to be LCA, but only one condition needs to met for it to return true in the DFS, because at least if one condition is true, we can have an hope that the second subtree or the current node or anything could make up the second condition to be true, right? So, and because of that, we are going to be explicitly defining a variable that is going to help us to keep track that, okay, if 2 conditions met, definitely we found in the LCA, and we're going to be calling that variable the LCA, right? Okay, let's make it global here, global LCA. So after calling this function down here, we just want to hope that the LCA have been found, and then we just return LCA. So we hope that in the process of recursively calling the DFS, we are gonna find the LCA and we are gonna rename it to a more satisfying node that appears to be the LCA, and then we're gonna return it. So that's what this function lowest common ancestor is doing. So let's define the function DFS now, which actually represents the depth first search. So the actually the recursive method we are gonna be using. Okay, our root now. So it's going to be taking a node which is going to be a tree node. It's going to be taking a P, which is one of the nodes that we are finding their ancestor. So there's going to be a Q as well, representing the second node which we are finding their common ancestor. So this is going to be a boolean, don't forget. So it's just a boolean return true or false. Okay, if not none, so in a situation like this we want to return false. The reason why is because there's no how if not node return false, because there's no how a non object will be the ancestor, or we even have a possibility or edge of being Q or P, right? It cannot be P, cannot be Q, it cannot be common ancestor. So we just want to return false for that. Okay, now let's collect is P or Q. So to check if this is when it is not node, it is not none. Don't forget we already returned false had it been it is none, but now if it is not none, we want to check if node is equals to P or node equals to Q. You don't need to worry that why are we doing P or Q. Well, there's a distinction between P and Q, so it can either be P or Q. It cannot be both P or Q, P and Q. So it's just fine as we see that node equals to P or node equals to Q. So because we know that even if this is one out of P or Q, we still have another one to search. So okay, if this is just gonna collect a true or false whether node is P or Q. All right, let's go collect the left node now. So by actually calling DFS on the left subtree, right? So which is node dot left. So to check if the left node is also containing P or Q. So we're gonna pass in P and Q to it, right? So also we're gonna define the right node, so to be equals to DFS of node dot right, node dot right P and Q. So now one thing you need to know is that we just need 3 of this function to be true, 2 out of these 3 functions to be true. You understand? So if don't forget that they are all boolean, all of them are gonna return either a true or false. So if it's P or Q plus left node, so they are all boolean. So don't forget that boolean also actually means 1 and 0. True means 1, false means 0. So that's why I'm using this addition. So I just want to check if is equals to 2, that is if 2 satisfy out of the 3. Don't forget that the 3 of them can never be satisfied, right? Because the nodes in the tree are unique. That's given to us in the problem statement as a constraint. So there's no how P and Q want to fit into 3 positions: the current node, the left and the right node. So the highest we have is 2, and that's exactly what we are looking for. And if it is 2, definitely we found the LCA at this particular node, right? If 2 is satisfied. But if 2 is not satisfied, but we just want to check if at least 1 is satisfied now. If this or left node or right node, that is if 1 is satisfied, fine. What I want to do is that I want to return true as well. If at least 1 is satisfied, this actually means at least 1. Even if it's 2 that is satisfied, it's going to return true. So, and that means that okay, at least we've actually found one of P or Q in this particular subtree. So otherwise just return false. So meaning that it's not even it doesn't exist in that subtree at all, and it is not a LC as well. So, and this is simply all we need to do actually, and we just hope that we're gonna find our LCA one day and return it. So let's run this code now. It's just as simple as that, really. But let's see how it goes. Okay, there's going to be an error, at least because we never made them. We never set this to global here. GLOBAL. global LCA. So we have to set it to global so that we can use it so that we can easily use it inside this function. But even this thing return none. Why? Let me run it again. Okay, a tree node is returned now. So let's see if it is the particular. Don't forget that this problem that I'm actually putting forward here is the same on the screen that you can see. Okay, it's the same here. So, and the return value is 3 because 3 is the LCA, right? So let's run the code again and see if it's going to return 3. So I try to print the value. So don't forget that the lowest common ancestor actually called the DFS function, and after the whole call is going to return LCA. So with also hoping that the LCA will have been found, and it's just going to return that updated LCA value. So if you can see here, 3 is being printed, of course, and actually we got the answer right. Sorry, we got the answer right, and this is the 3 printed. So this is how to solve this problem. It's actually logic, simply logic, and I really hope you understand this. Kindly do well to like, comment, and subscribe to my YouTube channel, please. Thank you.